We have already seen the 180 degrees conduction mode of a three-phase inverter in the previous video. The link is given in the description. Please go through it. Now we'll see how a three-phase inverter works in 120 degrees conduction mode. In this type of control, each transistor conducts for 120 degrees. Only two transistors remains on at any instant of time. The gating signals for this 120 degrees conduction mode will be the gating signal of the first transistor will be for 120 degrees, then it will stop, and the gain at 2 pi it starts for 120 degrees. Gating signal of G2 will start at 60 degrees and remains on for next 120 degrees, then here also in the next cycle turns on. Then G3 will turn on at 120, remains on for next 120 degrees here and remains on for 120 degrees. Next, the G5 will turn on after 60 degrees, remains on for 120 degrees. And G6 will turn on at 5 pi by 3 and remains on for next 120 degrees. Then this will be turned on before also for 60 degrees. The conduction sequence of transistors is 6 1, 1 2, 2 3, 3 4, 4 5, 5 6, 6 1. There are 6 modes of operation in one cycle. So mode 1 for Y connected load, you observe A, so neutral, phase B and phase C, this is Vs, load R. Then the VIN equals to the total voltage Vs divided by half, and VBN equals to minus Vs by 2 as the current flows from A to B, and VCN equals to 0. This is for from 0 less than or equal to omega t less than or equal to pi by 3. For mode 2, from pi by 3 to 2 pi by 3. Here the A is connected and C is connected between the voltage Vs, A, B, C terminals. So B is left alone. Then VIN equals to Vs by 2, VCN equals to the current flows in this direction, VCN equals to minus Vs by 2, and VBN equals to 0. Mode 3 between 2 pi by 3 and pi. So Vs connected between B and C is left alone. Then VIN equals to 0, VBN equals to Vs by 2, VCN equals to minus Vs by 2. Mode 4 is between pi and 4 pi by 3. The equivalent circuit, C is left alone, and B is having positive voltage and A is having negative voltage Vs. The current direction is reversed BA. Then VIN equals to minus Vs by 2, VBN equals to Vs by 2, and VCN equals to 0. Mode 5 is in between 4 pi by 3 and 5 pi by 3. Neutral A, B, and C. Now B is left alone. Then C is having positive voltage, A is having negative voltage. B don't have any connection, then this is my Vs. The current flows from C to A. Then VCN equals to Vs by 2, VIN equals to minus Vs by 2, and VBN equals to 0. Mode 6. This is in between 5 pi by 3 and 6 pi by 3, which is nothing but 2 pi. Vs, C to B is left alone, B, C. Then the voltage VCN is positive, that is Vs by 2, VBN equals to minus Vs by 2, and VAN equals to 0. This completes one cycle. So in the next cycle, same modes of operation will be there. Let us show these values in a waveform VAN and VBN and VCN. So these are the waveforms for VAN, VBN and VCN. Line to neutral voltage can be expressed in Fourier series. That VAN equals to sigma n 1352 infinity 2 Vs by n pi cos n pi by 6 sine n of omega t plus pi by 6. Question number 1. Then VBN equals to sigma n equals to 1352 infinity 2 Vs by n pi cos n pi by 6 sine n of omega t minus pi by 2. Second equation. Then VCN equals to sigma n equals to 135 into infinity 2 Vs by n pi cos n pi by 6 sine n of omega t minus 7 pi by 6. That is equation number 3. Now the line A to B voltage is equals to VAB to 3 times of VAN with a phase advancement of 30 degrees. There is a delay of pi by 6 between the turning off of Q1 and Q4. Thus, there should be no short circuit of the DC supply through one upper and one lower transistor. At any time, two load terminals are connected to the DC supply and the third one remains open. The potential of this open terminal will depend on the load characteristics and would be unpredictable. Since one transistor conducts for 120 degrees, the transistors are less utilized as compared to the 180 degrees conduction for the same load condition. This is regarding 120 degrees conduction mode of operation of the three-phase inverter. If this video is useful, please like, share and subscribe.